Hello students, happy morning. Myself Muniraju Naidu, Assistant Professor, Department of Computer Science and Engineering, working at Institute of Aeronautical Engineering, Hyderabad. So in this video, I'm going to discuss about process concepts in operating system. So in the previous videos, already we discussed what is operating system, what is the importance of operating system, and what are the various objectives of operating system, functions of operating system, services provided by the operating system, and what are the various categories of operating systems. So now coming to this process concepts. So what is meant by process and what is the importance of process, and what are the various states of process, and what is meant by PCB, process control block, and process scheduling. So let us start process concepts. So the introduction about the process concept, process state, process control block, and process scheduling. See, we know in any operating system, the process is a very important one, because whether that is command line user interface operating system or graphical user interface operating system, each and every operating system executes a number of programs, right? So that particular programs may be either batch systems as well as time shared systems. So depends upon our requirement here. Whenever the batch systems executes a number of programs, those are called as a jobs. Whereas coming to the time shared systems, which executes a number of programs, those are called as a tasks or user programs. So here we use the term either job as well as the process. So both are same. So simply say that according to the operating system, process is any program that is under execution. So a program in execution, and the process execution must progress in sequential fashion. So if you take any number of processes, right? So just you click on that Microsoft Word, then it assumes that according to the operating system, it is one particular process. So once you click on that particular process, so it automatically creates some space to that particular process, and it creates one PCB, process control block. So whatever the task we are going to execute within that particular process, so the process execution must progress in sequential fashion. So based on this introduction, each and every process which includes program counter, stack, and data section. So in addition to that, there are a number of parameters, but the process takes into the consideration the program counter, stack, as well as the data section. So we know whenever each and every program which consists of a number of sections, right? So you know the documentation section, then coding section, right? So each and every the program code, which is also called as a text section here. Now, whatever the current activity which includes PC in the sense program counter, processor registers, right? So, based upon the program counter and processor registers, the operating system identifies that what is the state of that particular process. So, whenever any particular program which consists of a number of parts, automatically one particular part we can call it as a stack, which contains the temporary data, right? So that particular temporary data which includes parameters like functional parameters and addresses, return addresses, as well as the variables, local variables. So local variables, return addresses, and function parameters, these are includes in the stack section. Whereas the data section which contains the global variables. So wherever you can use that particular global variables, so we need to store that particular global variables into the data section. Then the heap memory which contains the memory dynamically allocated during the runtime. So each and every program which consists of multiple parts, right? So the major part we can call as a code. So code is also called as a text section. Then whatever the current activity which includes the program counter as well as the PR, processor registers. Now the stack contains the temporary data like local variables, return addresses and function parameters. Then data section which contains the global variables. So program is a passive entity whereas a process is active. So whenever the program is a passive entity, we can term it as the process is in active state. So that means the program becomes process when exe file loaded into the memory, right? So program becomes process whenever executable file loaded into the memory. So we know in most of the languages, the execution of each and every program started via graphical user interfaces like mouse clicks or command line entry of its name, file name, whatever it is. So the execution of program started with the help of some command. That particular commands may be either in graphical user interface or command line interface. So both are same in the sense of how the program is executed. So each and every program which consists of number of processes, right? So that means several processes in the sense, for example, I want to execute one application, right? So simple example. So my task is I need to prepare my resume and take the printout. So this particular task which consists of two set of processes. First set is with the help of any Microsoft Word or whatever the tool, right? So based on that, I need to prepare my biodata. Then with the help of one particular resource, we can call as a physical resource type like printer. So whatever I prepared, the same document I need to take the printout. So these are the various tasks or processes. So consider multiple users executing the same program. So in general, in real-time applications, there's a same thing happens, right? So the same program that may be executed by number of users, right? So there is no guarantee that all the users located in the same region, right? So in this scenario, how the memory which stores that particular process. See here, this is the process in memory, right? So depends upon that particular process, it occupies the space. For example, let us consider in our simple example. So whenever we need to just click on that Microsoft Word, right? So before starting my preparation of my resume, just I need to open that Microsoft Word, right? At that time, the process created. The operating system creates one particular process. So that particular process stores that 0 KB space, right? So whenever I need to insert some information into that particular Word, automatically, whatever the size of that particular Word file, which increases. Is it right? So that is we can call as a process in memory. See here, 0 to max. This is the max, right? So here number of, there are multiple parts in each and every process. Those are we can call as a sections, like a text section, that is for documentation, data, heap and user section, as well as the stack, right? So this is we can call as a process in memory. Now coming to the process state. Process state. So what is meant by process state? So if you take any type of operating system like graphical user interface operating systems or else command line user interface operating systems, right? So each and every operating system must execute some set of processes, right? But internally there exists a number of states related to the process, right? So those are actually we can call as a 5-state process model. So those 5 states are new. Those 5 states are new, running, waiting, ready, and terminated. So these are the 5 states. So new, just the process is being created. Just like just you need to double click on Microsoft Word, just automatically that is a process is created. So we can call it that is a new state. The process is being created. Then running. So instructions are being executed. So once you type into that particular Microsoft Word, right? So automatically the instructions are being executed. In the sense that particular process changes its state from new to ready. Sorry, running. New to running. So if that particular process is waiting for some event, like for example, as per our previous example, just I finished my biodata, creation of biodata. Then automatically I need to take the printout. So once I request to the printer, at that time the printer is busy with some other process, then automatically my process enters into the waiting state. So that is here we can call as a waiting state. The process is waiting for some event to occur. If the printer is free, then only my process again changes its states from waiting state to the running state. But before that, waiting to running, there exists one state called as a ready state. So the process is waiting to be assigned to a processor. So there are a number of processes which are under waiting. So those are comes under the ready queue, right? So if the processor is ready to execute any one of the process, then the processor picks that particular process from the ready queue, then automatically the process changes its state. So ready means the process is waiting to be assigned to a processor. So finally terminated. So whatever the work is completed, then automatically the process has finished its execution. So this is very important in case of process states, because based on this 5-state process model, in the future we are going to discuss about the scheduling algorithms, right? So new, the process is being created. Running in the sense instructions are being executed. Waiting in the sense the process is waiting for some event to occur. Then ready, the process is waiting to be assigned to a processor. And finally terminated, the process has finished its execution. See here, this is the, we can call as a 5-state process model, diagram of process states, which includes the 5 states, right? See, the first one is new, right? Ready, running, waiting, terminated. See here, once the process is just created, there is a new, the change of its state, that is a just created, we can call as a new. Then if anything happens to that particular process, like starts the execution, something, then it enters into the ready state. So that means the same process changes its state from new to ready, right? So then it's time to that particular process to execute. Then that is we can call as a scheduler dispatch. Scheduler dispatch. So automatically it changes its state from ready to running, right? So if anything happens, in the sense that particular process is waiting for something, right, or else any interrupt occurs, then automatically it changes its state from running to interrupt. It's waiting for something, then it changes its states from running to waiting. See here, input or output event wait. Then if that particular process, whatever the processes which are under the waiting states, right, it's those turn to execute, then those processes changes their states from waiting to ready. So that is input output or event completion. So finally see here, always each and every process terminates from the running state to the terminated state, right? After successful execution of our process, then it exit, right? So this is the diagram of a 5-state process model: new, ready, running, waiting, as well as the terminated. Then PCB, process control block. So we know PCB, previously heard this term in the computer organization. So that's why this is the prerequisite for operating systems. Computer organization is a prerequisite for operating systems. So they are PCB in the sense printed circuit board, right? So just like our motherboard, right? So what happens in case of printed circuit board, on one particular board, you need to design how that particular board, or we can call it the architecture of that particular processor and whatever the storage devices, right? So how those are incorporated to each other, right? So in the same way, whatever the pictorial representation on any particular board. So exactly the back side we need to arrange those components, right? So that is a printed circuit board, right? So the best examples for printed circuit boards are motherboards and whatever the boards you are seeing in remotes as well as the mobile phones, etc. Similarly, the operating system, according to the process concepts, the operating system uses the PCB. Here, PCB in the sense process control block. Process control block. Right? So each and every PCB. So just whenever one particular process is created, then automatically the operating system creates one PCB for that particular process. Right? So that particular PCB which contains some fields or some parameters, which includes process state. Right? Before that process ID is there. Right? So that is process ID, then process state, program counter, CPU registers, scheduling information, memory management information, accounting information, IO information, and finally it stores the process context. Process context. Right? So this particular information which is associated with each and every process. So, in real-time applications, the operating system creates a number of processes. Operating system creates number of processes. For each and every process, there exists one PCB, process control block. See, this is the representation of process control block, right? So, process state, process number, program counter, registers, memory limits, as well as the list of open files. Right? Process state, process number, program counter, registers, memory limits, as well as the list of open files. Now, how the processor switches from one process to another process. Right? For example, if you take a Windows operating system, here we are able to see, right? So whether I am going to use this particular screen, right? Either in the full screen mode, right? Or else just simply yes, like this, either full screen mode or simply I need to take into that half screen mode, right? So this is already you are able to see in Windows operating system. But how the processor identifies that what type of actions you are going to perform on this particular process. Right. So nowadays we can call as a multi-user operating systems as well as a time-sharing system, multitasking systems. Right. So single user can capable of executing more number of processes at a time. Right. So meanwhile, how the processor switches from one process to another process within a fraction of seconds. Right. So let us take some example here. We consider only two processes like process P0 and process P1. Right. So now this is the operating system. This is the operating system. So once the process P0 just it starts the execution. It starts the execution. So it executes and up to whenever any interrupt occurs. If any interrupt occurs, then automatically whatever the process which is under execution, so that particular process save that state and it enters into the waiting state. So that means some interrupt is there, right? Or system call we can call as a. So that is we can call as a the save. That particular process save its state where into the PCB of process first process. So here we can consider the process P0. So process P0 automatically the PCB related to that particular process, that is a PCB 0. So another one process 1 P1. So the PCB for that process 1 that is different. So now the process P0 that is save its state into its PCB. Right. See, until that particular process is executing, here the process P1 is no more. Is it right? So once now the process P1 is entered into that queue, then the change of its state, that is we can call as a idle. The process P1 is idle. right? So then after some particular period of time, so the process P0, right, reload the state from PCB1. So now it's time to execute that particular process. So that is here we can represent it here executing, right? So until that particular period, this is a ideal state of process P0. So like this, each and every processor switches from one process to another process. So just this is for example, you can consider only two processes, but in real-time applications, there are n number of processes, right? So how fastly each and every process which changes its state with the help of that particular processor. That deals about the CPU switches from one process to another process. Then process scheduling, right? So scheduling is very important in operating system concepts, because how the processor schedules the processes, right? So that means at what time this particular process is going to be executed, at what time this particular process is going to be executed, right? So here the processor schedules which process comes under the execution. So what is the next process, right? So in addition to that, here one point you need to remember, that is always we need to utilize the processor very efficiently. Is it right? So that's why here we can call as a maximize the CPU usage and quickly switch processes onto CPU for time sharing basis. Right? So already we know that each and every processor can capable of executing multiple processes. Right? So that means maximize the processor usage, at the same time quickly the switch processes from one process to another processes. Right? So here the process scheduler which selects among available processes for next execution on CPU, right? So that is very important here, right? So how the processor selects the process, from where the processor access the available processes. See, there exists one job pool, right? So within that particular job pool, whatever the processes those are ready to execute, so those processes enters into that particular job pool. So the process scheduler selects among available processes for next execution on CPU, right? Then here each and every process maintains some scheduling queues of process. So each and every CPU, or else we can call it as a processor, which maintains scheduling queues of processes. Right? That particular scheduling queues which consists of job queue, ready queue, as well as the device queues, right? So just now we described that this is the job queue. So job queue is nothing but which consists of a set of all the processes in the system. So similarly, there exists one ready queue, right? So this particular ready queue which consists of a number of processes which are residing in the main memory. In the sense, those processes are ready and waiting to execute, right? So that means when compared to that job queue, the ready queue size is less. The ready queue size is less when compared to the job queue. Job queue is nothing but set of all the processes in the system, whether that particular process may be in the ready state or waiting state or running state, whatever it is. But whereas ready queue in the sense, set of all processes residing in the main memory which are ready and waiting to execute. Then device queues. So device queues which are set of processes waiting for an input-output device. Set of processes which are waiting for an only input-output device. So automatically the device queue is also less when compared to the request queue as well as the job queue. So each and every time the processes migrate among the various queues. See, for example, let us take one example. So the process representation in a Linux operating system, right? So here we need to consider the represented that particular process by the C structure, that is a task underscore struct, right? So the PCB concept. So whenever any type of operating system, like you take a command line user interface, the best example is a Linux operating system. Right? How we need to represent each and every process in a Linux operating system, right? See, we know with the help of the process ID. So here we need to represent PID space T, that is a task underscore struct, and space PID, process identifier. then the state of that particular process, then scheduling information. Scheduling information is assigned like this, unsigned int time slice. Then which one is the parent process and which one is the children process, and how many files are there, and among those how many are open files, and what is the address space of that particular program. See here, this is the struct task underscore struct process information. Here this is a current executing process, right? Here we identify that the process information. Like this, here we need to represent each and every process in Linux operating system. Then how the ready queues and various input output device queues are managed, right? So initially the job queue is there, job queue which consists of set of all the processes, whereas a ready queue is just which consists of processes which are residing in the main memory, which are ready as well as waiting to execute. Similarly, device queues. So only the set of processes waiting for an input output device. So that is the device queue, right? So see here, initially we have ready queue. That particular ready queue is having the queue header, right? So we know head tile which stores some information regarding that particular processes. Right? So each and every process which maintains some process control block. For example, let us take this is a process control block which is related to the process 7. This is a process control block related to the process 2. Then another storage area, that is a magnetic tape, right? Another one, magnetic tape 1. So then disk. So again here various PCBs. That means various processes are executing with the help of the disk. Finally, the terminal. Like this, various ready queues as well as the input output device queues are executing with the help of any particular processor. Now, how the representation of each and every process scheduling, right? See, first of all, each and every process enters into the ready queue, right? So whenever the particular process enters into the ready queue, automatically the processor fetches that particular process, and the processor is ready to execute that particular process. Right? How the processor is going to execute, either with the help of input output request or time slice expired, or we can call as some operating systems we can call as a fork a child as well as the wait for an interrupt. So fork a child means here the child process is executes, wait for an interrupt means interrupt occurs. Right? If these two conditions are there, then automatically the particular process enters into the ready queue. Right? So before execution is done, that means the processor always accepts each and every process from the ready queue only. So that is, we need to represent various processes according to the scheduling. So here the processor is schedules, right? So now your turn, right? You are going to execute. Next, your turn, you are going to execute. If that particular process is waiting for some time or something, then automatically that is again enters into the ready queue. So that is representation of process scheduling. Then coming to the schedulers, right? So we have long-term schedulers as well as the short-term schedulers. So simply say that long-term schedulers are also called as a job schedulers, whereas short-term schedulers are also called as a processor schedulers, right? So what is meant by long-term scheduler, right? Here long-term schedulers in the sense the scheduler which selects among various processes should be brought into the ready queue. Right, so those are the simply we can call as a job scheduler. Selects which processes should be brought into the ready queue. Then CPU scheduler or short-term scheduler, which is called as a selects which processes should be executed next and allocates the CPU. Here, because we can call this a processor scheduler or CPU scheduler, short-term scheduler, selects which processes should be executed next and allocates the CPU. So sometimes the only scheduler in a system, that is we can call as a short-term scheduler, right? So but there is a small difference between short-term scheduler and long-term scheduler, right? So by default, the short-term scheduler is somewhat improves the performance. That means it is somewhat fast when compared to the long-term scheduler, because this is directly here the processor is directly involved in case of short-term scheduler. So short-term scheduler is invoked very frequently in the form of very fast, very less milliseconds. So whereas long-term scheduler is invoked very infrequently. That means it takes some time to execute, right? Because it searches various jobs. So the long-term scheduler which controls the degree of multi-programming, right? So this is the small difference between long-term scheduler as well as the short-term scheduler. So simply say that long-term scheduler, which is also called as a job scheduler, whereas short-term scheduler, which is also called as a processor scheduler. So the name itself specifies that processor scheduler. So automatically it executes a number of programs very frequently. So it may be fast when compared to the long-term scheduler, right? Now the processes can be described either input-output bound process or CPU bound process. What is meant by input-output bound process? Input-output bound process is it spends more time doing input-output than computations, because here there is no direct involvement of the processor. So input-output bound process which spends more time doing input-output than computations, whereas the processor bound process spends more time doing computations, right? So this is how the processes can be described according to that processes. See, this is the addition of medium-term scheduling. Addition of medium-term scheduling, right? So in addition to that, long-term scheduling as well as the short-term scheduling, there is a terminology called as a medium-term scheduling, right? So here we need to consider swap-in as well as the swap-out concept, right? So when we need to consider the swap-in, right? So whenever any particular process is partially executed, then automatically there is a swapped out process. Now again the processor takes that particular process into the ready queue. From ready queue again the processor accepts that particular process and it is going for the execution purpose, right? If any particular process is waiting for any input output, that is automatically enters into the input output waiting queue. So this is the representation of medium term scheduling. Now we know the context switch. Context switch is very important field in the PCB. You know, process control block which consists of process ID, process name, process state, etc. So among those, process context is also very important in the sense when the processor switches to the another process, right? So for example, there are number of processes are executing. The processor is capable of executing n number of processes. When the processor is executing n plus 1th process, so that is when the CPU switches to another process, the system must save the state of the old process and load the saved state for the new process via the context switch, right? So the best example I need to say for this understanding of context switch, right? Our previous example, like I need to prepare my resume with the help of any Word, right? Then I need to take the printout. Let us take my resume which consists of 20 pages, right? So I need to prepare with the help of MS Word and I am ready to take the printout with the help of the physical resource called as a printer. Now, whenever just I need to open that Microsoft Word, automatically my operating system creates one particular process to my resume, right? So then whenever I need to insert the instructions, I need to spend some time on my resume, then automatically the process size is also increased. Then whenever I need to take the printout, like for example, my resume which consists of 10 pages, like then what happens here, only 5 pages or the printer is capable of prints. Then any interrupt occurs, whether the cartridge is over or paper is jammed, something, then automatically what happens here, that particular state of that particular process is enters into the PCB. That is we can call as a context switch. So what happens here? So the processor identifies as something happens to that particular process. Then automatically it's save its state and it returns to me. That means it shows one dialog message. In the dialog box, it shows one message. What is that message? Hello user, your paper is jammed or your cartridge is not up to the mark. Something, right? So then again I need to execute some other process. Is it right? So then now I need to resolve that particular issue and again I need to take the printout. Now the process is executing from where it is stopped recently. So that means according to our example, my 5 papers are already printouts. Then it takes the next printout like from 6th page. So that is a context switch. So that is whenever the processor switches to another process, the system must save the state of the old process and loads the saved state for the new process via the context switch. So context of a process represented in the PCB. Context switch time is overheaded. The system doesn't useful any work while the switching. Right? So here the time is also dependent on the hardware support. Right? So that depends upon the configuration of each and every system. Here the PCBs are created. Then process creation. How the process creation. So depends upon various operating systems. Right, there are number of mechanisms to create any new process. Right, so here the parent process creates the children processes, which in turn creates another processor, which forms a tree of processes. So this is the parent process. These are the child processes. So here, how to identify each and every process? So generally with the help of the process identifier, the processor identifies that where that is process available, what is the size of that particular process, each and everything, just like our roll number. Then resource sharing. So either physical resources or logical resources must be shared to each and every process. So in the sense, parent as well as the children processes shares all the resources, but the children processors shares subset of parents resources. So whatever the resources which are already allocated to the parent nodes, only the children process just accept that particular resources from the parents. Right? Then parent and child share no resources. Right? So this is the resource sharing concept in multiple processes. Then execution. Parent and children executes concurrently. The parent node waits until the children terminate. The parent node waits until the children terminate. So similarly, the address space. Right? The child process which duplicates of parent, whereas the child has a program loaded into it. So here we need to easily identify what is the address space of each and every process. See, this is the process creation. So according to the operating systems, like for example, if you take the Unix operating system, see here, this is the fork is a system call. Here the parent node, which is the fork in the sense automatically the parent node is created, which waits for something, then automatically it resumes that particular process. Then the child node is created, so that is the executed. If it is completely executed, then finally it is the exit state. So the fork is a system call which creates a new process. According to the Unix operating system, the fork is a system call which creates a new process. Whereas execute, EXEC, is a system call which is used after a fork. That means once the new process is created, then only we need to perform some operation on that particular process. So execute is a system call which is used after a fork to replace the process memory space with a new program. So it depends upon the operating systems. Here we need to consider how various processes are executing. See, this is a simple C program forking separate processes, right? So what happens here, always process ID. So the main function starts with the process ID. So here we need to consider create another processes, right? That is a fork another process. If process ID equals to fork, then you need to consider that if process ID is less than 0, then automatically error is occurred. Else, if process ID is not less than 0 in the sense which is equal to 0, then automatically it creates a child process. Else, parent process. Like this, various operating systems. See, this is the Solaris operating system, how the various processes are created. So already we say that a set of nodes, or we can call it a parent process as well as a child process, those are identified with the help of the tree-based structure. See here, this is the scheduled process ID equals to 0, right? So then integer process ID 1, process ID 2, page out, fs flush process ID 3. So that means, see here, this is any real-time example. Here just you can go through that. The process ID in the sense C8105. That means this particular system is capable of executing more than 8,000 processes. Right? Then process termination. So finally, the terminated state. So the process executes last statement and asks the operating system to delete it. right? So if it is successful, then output data from child to the parent, right? If it is not successful, we can simply call it about the operation. So that is the processes resources are deallocated by the operating system. So one thing you have to remember, in general, any operating system gives access to the resources to any number of users, like request, use, and release. So first of all, you need to send a request to use that particular resource. If the particular resource is free, then automatically it allocates to you. Then automatically we need to use that particular resource. After completion of our work, definitely you need to release that particular resource, right? So processes, resources are deallocated by the operating system. Now the parent node may terminate the execution of the children processes. That is, we can call as a abort. So child nodes has exceeded allocated resources, then automatically whatever the task which is assigned to the child node, that is no longer required. If parent node is exiting, then what happens? Some operating systems do not allow child to continue if this parent is terminated. So that means the root node is no longer to execute. Then how the child nodes are going to be executed? So here we can call as a all children nodes are terminated. That particular operation here we can call as a cascading termination. Cascading termination. So this is a process concept. So in this video already we discussed that. So what is meant by process, and what is a process concept, and what is a PCB, and what are the various schedulers like long-term scheduler as well as the short-term scheduler, right? So within that particular process concept, 5-state process model like new, ready, running, waiting, as well as the terminated. So this is a process concept. So in the next video, I'm going to discuss about scheduling. What is meant by scheduling and what are the various scheduling algorithms, right? Thank you.
Like, share and subscribe. Hit the bell icon for more updates.